This is the first problem that I do for chapter 20, and it looks kind of finished. In fact, it is. I had recorded it, and then what happened, for some reason, it didn't want to save my recording, so I had to start over again, and I might as well leave what I had already written on there. Okay, so it says that a battery charger is connected to a dead battery and delivers a current of 6.0 amps for 5.0 hours, keeping the voltage across the battery terminals of at 12 volts in the process. How much energy is delivered to the battery? And so this is the information that is given in the problem. And in order to be in standard units, this one would have to be converted to seconds. Of course, 5 times 3,600 is those 18,000 seconds. Energy is what's asked for. What you find in the chapter is that power equals electric current times voltage, and then you have to go back to the energy chapter perhaps, where it says that energy is power times time, and that's pretty much it. Electric current times voltage times time, and then you get that in joules. And if you look at these three numbers here, 12 times 6 times 18,000 is probably going to be about a million joules. And when I had recorded it the first time, the one that I recorded that I lost, it really just took me also just 2 minutes for that. Down here, I introduced that you can do it a second way. From the previous chapter, you saw that either the previous chapter or the one before, it said that electric potential energy equals charge times potential, and so energy is equals charge times voltage. And then what happens is, because they don't give us the charge, but we know that electric current, this part here, and I can use a different color as well, this part here, electric current is charge per time, and then I just multiply that by time on both sides, so that time divides out and I can substitute the charge, and I come up with the same thing. I substitute electric current times time and come up with electric current times voltage times time. So the equation that is needed can be arrived at in two different ways. All right, next problem. I had also already started it. This one is really straightforward. It says high voltage power lines are familiar sight throughout the country. The aluminum wire used for some of these lines has a cross-sectional area of 4.9 times 10 to the negative 4 square meters. What is the resistance of 10 kilometers of this wire? So that's just a matter of plugging in numbers. Use the equation that connects resistance with resistivity. Plug in the numbers. The area is given in square meters in the problem. The length is 10 kilometers, respectively 10,000 meters. And the resistivity, you look up in the chapter, it lists it for aluminum as 2.82 times 10 to the negative 8 ohm meters. Units, the meters or meter squared will divide out, and you're just going to be left with ohms. I want to show that FET actually lists this kind of problem, or I'm not sorry, not this kind of problem, but has an applet that this problem can be done with. So here it is. Physics Educational Technology from Colorado. It's easy to Google. And the one I'm looking for, and here I already went into physics, electricity, magnets, and circuits. And the one that I want to look at is resistance in a wire. Click on Run Now. There it is. And now I'm going to look at what I get from the book. The resistivity is 2.82 ohm meters, but I don't have that available. Notice that it gives me ohm centimeters, so I'm just going to do 0.82. There we go, which means I have to have a conversion from that to ohm meters. And then the length here, yeah, I don't have kilometers, I only have centimeters, so this one here is actually centimeters. And then it lists in the problem 4.9 square centimeters. But as much as I try to shift, the closest I can get is the 4.85, and then it course, here the wire change, you know, you increase the length, that's kind of obvious, and the resistance increases, and the resistivity increases, so there are more atoms in here, and so the resistance increases back to the point to 828, and then the square area increases, and you can see it's easier for the electrons to flow through there, so the resistance goes down. But I put it back to, what was it again, 4.85, and again, this one is in centimeters, and you would have to multiply so and so much in order to get it to 10,000 meters. But overall, actually, these two, 5.8, because my numbers are so close here as far as the digits are concerned, it should contain a 5.8 in for the result, and then the decimal point might be a little bit off, or it might be actually the same if you convert all these centimeters to meters. In any case, just wanted to show that that one is available on FET. For this one here, the resistance is relatively small, but we have to look at that in power lines. And by the way, this is on top of the problem. This is doing something on top of it. We have to look at that, well, there is some kind of energy loss in there, or power loss, which of course is times time. So the power lines take up some energy. And in the previous problem, I wrote this as electric current times voltage times time. And now they give us the resistance in the wire, so I'm going to use the Ohm's law and plug it in as that voltage equals current times resistance. So another I times R, which makes this one here an I squared, and R times time. And since in the power lines we like to use up as little power or energy as possible, of course the resistance should be small. One way of achieving that is make pretty thick power lines. And the other one is that the current should be pretty small, and that's why you see such high voltages on the power lines, because that high voltage, after it goes through a transformer from the power plant, the voltage is being stepped up, but the electric current is being stepped down in order to get as little of a electric current running through the wire as possible with, well, a very high voltage at the same time, so that the power loss within the power lines is relatively small. That's just on top of what the problem asked about, but I figured, hey, this is a problem on power lines, so I might as well mention that. The next problem says a blow dryer and a vacuum cleaner each operate with voltage of 120 volts. The current rating of the blow dryer is 11 amps and that of the vacuum cleaner is 4.0 amps. Determine the power consumed A by the blow dryer and B the vacuum cleaner. C, determine the ratio of the energy used by the blow dryer in 50 minutes to the energy used by a vacuum cleaner in 1/2 hour. All of this is really straightforward. So the power for the, let's see, which one was the first one here, blow dryer. Yes, so for the blow dryer, BD, I guess. Whoops. BD equals electric current times voltage. Both numbers are given in the problem, so just plug them in. Once again, 120 volts times 11 amps, so you should come up with 1300 watts. For the vacuum cleaner, VC, same thing. Electric current is given as 4.0 amps. Voltage is the same as the blow dryer, 120 volts. So that should come out to 480 watts. Those were parts A and B. That was supposed to be an A, and that's a B. And part C is determine the ratio of how much one uses over the other, but they're run at different times. So that would mean the power of the blow dryer times the time that it's being used, and it was the 15 minutes respectively. Yeah, so for 15 minutes respectively 900 seconds, divide by the power for the vacuum cleaner. That was just calculated times the time for 30 minutes. That was supposed to be a 3 a moment ago, which is 1,800 seconds, and then equals, and then you're going to come up with so and so much more by the blow dry compared to vacuum cleaner with no units because a ratio doesn't have units. The next problem says an electric furnace runs 9 hours a day to heat a house during January 31 days. The heating element has a resistance of 5.3 ohms and carries a current of 25 amps. The cost of electricity is 10 cents or $0.10 per kilowatt hour. Find the cost of running the furnace for the month of January. Alright, notice that time is given, 9 hours times 31 days, and then we could argue if we're going to get the hours into seconds. I'll show that we don't have to in a moment. And the resistance is given and the current is given. That sounds like we have to use the power equation. So electric power equals electric current squared times resistance. Notice that the voltage isn't given. And then at some point we're going to have to come up with how much energy is being used. Well, that's where the time comes in. So of course E equals power times time, which means we have to use this kind of equation here, I squared times R times T. And of course what they're asking about is the total cost. Let's see, I'm going to start over. I wanted to write total cost. So the total cost there we go. Equals the rating they give us here, the 10 cents per kilowatt hour. Well, the kilowatt hour is a unit for energy. You know, the watt is in here times time. That comes out to energy. It's not the standard scientific unit, but it can be easily related to the joules with a certain conversion factor. In fact, the conversion factor would be 3.6 million. And so I would have to multiply this here by the energy that we would be calculating in order to get rid of this unit here. My energy up here will be perhaps in joules or kilowatt hours, and then the unit would divide out. So at this point here, it's a matter of plugging in numbers. The current is given as 25 amps. The resistance is given as 5.3 ohms, so 25 squared times 5.3. The time I mentioned a moment ago is given in hours times days, so 9 hours times 31 days would be 279 hours. I would keep this one here in hours because when it comes to converting, you really don't need to because it already says watt hours. So when you keep it in hours, actually what you're going to come up with here is not joules but watt hours. Only if I converted that hour here to seconds, then I would get joules, but I might as well leave it like this. So I come up here with watt hours, and then I shift the decimal point 3 times, and I come up with kilowatt hours, which then divides this unit here. And so I plug that in. Basically, you come up here at watt hours converted, shift the decimal point 3 times because of the kilo, multiply by $0.1, and you're going to come up with the total cost. And that would be in dollars. And on your energy bill, that's actually what you see is how many kilowatt hours you have been using. this one here, the result should be in the neighborhood of about $100 when you're done with it. This is a problem involving parallel resistances, and it says, what resistance must be placed in parallel with a 155 ohm resistor to make the equivalent resistance 115 ohms. So first I'm going to draw a little bit here. Here I'm going to make myself a battery. I don't know where to start here. And then I may want to draw some wires in here. There we go. Actually all the way across here. There, and then I'm going to put a resistor here, and in parallel I'm going to put a resistor here. And sorry that didn't quite line up here. There we go. Looks a little nicer. Now I have to try to squiggly my resistors in here. There we go. And one of them has a resistance of 155 ohms, and the other one is an unknown. Let's call this one R1, and we call this one R2. But what is given in the problem is that R total, or equivalent, is 115 ohms. There. Okay, well, this is parallel circuits. I do this one as a problem here for parallel circuits because for series circuits it's kind of trivial. Just plug in, add 3 numbers for 3 resistors, so I might as well do parallel circuits because they're a little tougher. It's not just add the resistors, but add the reciprocals. So 1R total equals 1 over R1 plus 1 over R2. And in this case, this one here is the unknown. So I do the algebra for that one. Therefore 1 over R1 equals 1 over the R total minus, as I get this here to the other side, minus 1 over R2. And then it's just a matter of plugging in numbers, looking for my calculator on my desk. So what I do is 1 over 115 should be the total, minus 1 over 155, and I come up with 0.002244. And when you come up with such a tiny number, then that tells you that you have to do one more step, and that is invert it, because what I just calculated is the reciprocal, so you have to invert it because of this one here in order to get R1. So I take that 0.002244 and divide it into 1, and I come up with 446 ohms. And so I actually gave the answer away for this problem here. Let me show you with a circuit construction, and I'm actually not going to use the FET circuit because I noticed when I used their circuit construction kits, that doesn't allow me to get up to 155 ohms, only to 100 ohms. So I would have to kind of use numbers like 15.5. In order to avoid that, I Google another circuit applet and that's really what I type in. And the one that I do like is this one here. And at this point there's a little bit of too much in here. I don't know how to erase everything. I'm going to put a resistor right here, and it asked me to put in a resistance, so I'm going to put in 155 ohms, and then apparently I have to change this one here to my calculated 446 ohms. I don't know why this one goes to the back now. It's a little odd. Okay, so 446 ohms. And then it doesn't allow me to simply measure the equivalent resistance. Oh, by the way, I have to take this one away. So what I do is I put a voltage source in here, a power source, and I put that voltage source as 115 volts, and I'll show you in a moment why I did that. Let me just put one more wire in here, and then let me put an ammeter here in order to determine the total electric current. So let me show you why I put 115 volts on there. Of course, resistance times electric current equals voltage, so that is Ohm's law. And for the total resistance I should come up with 115 ohms. And if I put a battery on there that supplies 115 volts, then I would know that I would have to measure 1 amp, and that's what I'm going to try to do, measure 1 amp. Let's see, there we go. And I'm going to click on this one here, and it says display ammeter. Yeah, that's the one I want. And indeed, I think this is close enough. 0.9989 amps. That's 1 amp. And the negative here is simply, let me get rid of that negative, because I can turn the ammeter around. Notice it says plus on the top, negative on the bottom. I changed polarity. No, that switched. So that really didn't matter. And now it's a positive number. So 0.9989 amps is what I'm measuring of 446 ohms and 155 ohms, which means that I have to have a total resistance of 115 ohms. There's a problem for determining the equivalent resistance in a series parallel combination circuit. In fact, that's all it says for the problem description. Determine the equivalent resistance between the points A and B for the group of resistors in the drawing. Okay, let's see. Let's analyze the circuit here first. The electric current goes in here. Here's a junction. So it goes through here. I need to click on that. It splits up here, and it splits up there, which means whatever comes after that must be in parallel with this one. So all of the stuff here on the right hand side can be considered in parallel with this one. In fact, the current flows through here, flows through here, flows through here, flows through here, comes back to this junction here where it rejoins the other part of the current that it split up from, and then comes back to be the same current. So this resistor is in parallel with everything else. In order to do anything here, well, I first have to look at all these other resistors. Okay, so let's look at the 3.0 ohm resistor. Well, after that, the current splits up, but notice the current goes through here, and then it splits up here, 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 comes all back together, and here it's the same current that it was prior to splitting up. So these two here, this one here, and all the rest here that come after the 3 ohm resistor are actually in series with each other. And again, I cannot do anything with the 3 ohm resistor until I have looked at all of these here. These two resistors are actually the easiest in the bunch. Not only do they look parallel, but they are parallel. The current goes in here, splits up, and then comes back together here, and these two are clearly in parallel. These here, if you think about it, this one here, and this one here are totally in series. Sure, they don't look like it in the drawing, but that's just the way the drawing was done. Current goes through here, and then the same current goes through there. So these two are in series. You can draw them here and here, or you can draw one up here and one to the side, or you can draw both of them here on the side. It's all the same. These two are in series. Where to start? Well, either start with these two here in series or start with these two in parallel, but I'll show you in a moment why I start with the two in series. So let me write that down. 4.0 ohms plus 6.0 ohms, trivial. I come up with 10.0 ohms. And now what I'm going to do is I'm going to take this circuit here and copy it, put it there, and I'm going to draw in that, instead of the 4 and 6 ohms in series, I have just one resistor here of 10.0 ohms. That was supposed to be a period. And this one here just goes straight through. There we go. And notice why I started with these two resistors here being in series, giving me 10 ohms, because now I realize that because of this junction here, which is virtually the same as this junction here now, or actually is, the current splits up into three parts. The current that comes in here goes through this one, goes through this one, goes through this one, and those three parts come back together. Here, and here, and here. So these three resistors are actually in parallel. And again, if I look at these two here to begin with, these two are indeed in parallel with this one and this one. What I did now is it saved me some effort realizing that these two here being in series, these two here together, the 10 ohms, are also in series with, in parallel with the 8 and the 9 ohms. So what I'm going to do next is change the color and say that 1 over 9.0 ohms plus 1 over 8.0 ohms plus 1 over 10.0 ohms is 1 over the equivalent resistance on the right hand side there, supposed to be Q. Type it onto my calculator. So I'm going to have 1 over 9 plus 1 over 8 plus 1 over 10. The result of that is 0.336. That small number tells me that I still have to invert it. That kind of decimal number almost always tells me that I still need to invert that. So I do that, and that is 2.98 ohms, maybe around at 3.0 ohms, but I keep my intermediate results in just one more significant figure and will round later on. So overall, again, I could copy this whole one here, and now I could say that I basically, let's see, I think I'm still in blue, I have a resistor here that is 2.98, at least maybe 2.98 ohms. These two here were in series. That gave me the 10 a while ago, and then I put the 10 into parallel with the 8 and the 9, so which means I totally have an equivalent here for this entire thing here on the right hand side of 2.98 ohms. And that one here is, notice I got rid of these two junctions here. This one here is now totally in series with the 3.0 ohms, as I mentioned earlier. All of this one here is in series with the 3 ohms, as I tried to explain, with the current going through here. The current goes through here. Sure, here it splits up because of these other resistors, but here it comes back together and it's the same current over here as it was here. It's the same current, total current flowing through all of these here together. I guess I could have just left it as 3.0 ohms because I notice it's in series with the 3.0. So on the right hand side here, obviously I have 6 ohms. Again, use a different color here. So I have a total of 6.0 ohms on the right hand side, and that one, as you can see, the current splits up here and then comes back together here, is then of course in parallel. So the total result is therefore 1 over 20.0 ohms plus 1 over 6.0 ohms equals, that is 1 over the total resistance. And that last step, I'll let you do that. Let's see what I want to write here. So therefore R total equals whatever you come up with in ohms. Remember, when you add these here, the reciprocals, you have to still, you come up with a small number, you have to still invert it in order to get the total resistance. A couple of things to say here. Notice that the equivalent resistance in this 3 resistor parallel part of the circuit here is smaller than the smallest one that was given here as the 8 ohms, and the same thing will happen here. The total resistance that you will get here will be smaller than the smallest one you have over here, which means smaller than 6.0 ohms. Keep that in mind. If you don't come up with a number that's smaller, you would have made a mistake. The other thing I wanted to mention is really when you analyze a combination circuit, it does involve several steps. You really have to go through each single part of the circuit at a time. So here the series part, then here the parallel part, then over here the series part, and then finally the parallel part here with the 6 ohms and the 20. For this one here, I actually will show that the circuit construction kit. I'll take a moment here, come up. Alright, grab a wire. Actually, I'll grab a resistor to begin with, and then I put another one, let's see, over here, and then there's one over here, and one there, and then there's a couple in the middle here. There we go. Whoops. And now I'll grab the wires. There we go, and there. Of course, my schematic looks in a certain way when I put it together. Overall, it's the same deal, but I want to see how much I can do with a certain amount of wires here, and actually I can do it like this here. I'll put a little wire in there to make it look better. If you look at it carefully, that's exactly the same circuit that you find in the book. Put a battery here. There we go. And oops. There we go. And I put an ammeter right there. There we go. But I still have to adjust the resistances. And let's see, the first one, this one here was 3 ohms. This one was 20 ohms. This one was, I right click on in order to change the resistance. This one was 9, and the next one will be 8. And then this one here was 4, and the one at the bottom is 6. And done. And let's see, I'm going to change the voltage just a little bit. I'm going to try 9.2 volts just for kicks. Yeah, oh, that's nice. 9.2 volts, remember? And I have 2 amps right here. Ohm's law tells me that the total resistance of the entire circuit is divide the total voltage by the total current. So 9.2 volts divided by 2 amps is 4.6 ohms, and that's what you should have come up with when you do go through the calculation that I showed you on paper earlier. This next problem is about Kirchhoff's rules, and it says determine the voltage across the 5.0 ohm resistor in the drawing. Which end of the resistor is at the higher potential? As you can see, well, there is a current flowing through the 5 ohm, and that splits up here and it goes in there, but notice there's a positive potential here, and then there's a positive potential kind of opposing them from the other side. So in which direction is the current actually flowing? For complicated circuits like these, Kirchhoff's rules, the junction rule and the loop rule, come in very handy, because here it's virtually impossible to determine what is parallel, what is series. If these two batteries weren't here, then we could actually do the problem, but they were there. So, I mean, we could do the problem with series and parallel circuits, but these two batteries are there, so we have to deal with them in a different way. I figured I'm going to start this problem out with actually doing the circuit on the FET circuit construction kit. And so I'm going to put a resistor here and there and there. And then I put a battery and another one and another one. And let's see, they're all turning up like this. Like that. And like that. There we go. And yeah, I could connect those two here. And then I can connect here, and I can connect here. You can see that from the drawing, that's exactly the same if I put the junction here or if I slide it over there. It's just a piece of wire in between, so that's exactly the same. And then over here I put a little wire there and a little wire here, and then I connect over here and over there. And there is my circuit, and interestingly enough, nothing happens on FET. Oh, maybe I should adjust certain things, such as the resistors. 5 ohms. And actually, I think I'm going to do the voltages first. It says 10 volts on this one. And, oh, there, something happens now. All right. And 2, and the other one was 15. There we go. And this one here is 10. And this one here is 10 as well. Oh, there it is, 10 as well. Okay. Well, that pretty much answers one already. That is, the current flows from here, from the positive to over here, the negative. Despite of that, this one is a positive terminal, but notice that battery is kind of opposing what, especially this battery here, which says what this battery produces. Interestingly enough, this is the highest voltage here. Oh, you know what? I have to think of something here. One moment. I have to look at FET, which way they actually put the current. If they put the current from the positive to negative, or if they show the electrons flowing. Oh, they show the electrons flowing. Okay, so the electrons are, of course, flowing from negative to positive, which means the positive end is over here and the negative end is over here. Again, as you learned in the book, that the electrons are flowing in one direction, but the electric current is defined as the opposite direction. So positive is here, negative is there. Respectively, this is at the higher potential than this one. Okay, overall they also want to figure out which end is a higher potential and turn the voltage across the 5 ohm resistor. So what I'm going to do is I'm going to grab myself a voltmeter. Oh, there it is, I guess. Put it there, and I put this one there, and I put that one there, and it reads 0.75 volts, and I'm done. That was actually relatively quickly to do, except that the proper way, I still have to do the proper way, and that's going to take a while because Kirchhoff's rules involve systems of equations. In this case, I will just use the systems of equations with substitution and elimination methods, or otherwise, if it becomes more complicated, one could use also matrices instead of systems of equations. But in any case, let's do it on paper. So the analysis, the proper analysis. There are 3 loops here and 2 junctions. The junctions are easy to see, 1 and 2. And the loops are, of course, the entire thing is one loop. And here on the left is one, and on the right is one. So 3 loops, 2 junctions. Setting up the equations for those currents and the voltages would produce 5 equations. Well, we would have to look at how many variables do we have, and therefore how many equations do we need. Well, they want us to figure out what the voltage is on this one. So that would be a variable, an unknown. Notice that we don't know what the voltage is on this one. We don't know what the voltage is on this one is. We don't have to figure them out. However, these are unknowns as well. So 1, 2, 3. We have 3 unknowns. We have 5 equations, which means actually we kind of have an overkill if we write them all down. Therefore, among those 5, we choose 3 to match the number of variables we got, and those are the ones that we write down. Among the 3 loops, it makes sense only to write 2 down. For example, we write the one here on the left down, and we write the one on the right down. If we also took the entire loop, well, you can see if you put the right loop and left loop together, you come up with the entire loop. So what that would mean is that the entire loop as an equation becomes redundant. You can just take the equation on the left and the equation on the right, put it together, you come up with the entire loop, so you haven't gained anything. So therefore, we're only going to write down the loop on the left, the loop on the right, and then one of the 2 junctions. And as far as one of the 2 junctions here, this one is a whole lot more comfortable to write down. The current going through this one here splitting up into these 2 components, or current going through this one here and splitting up to these 2 components. Okay, let's write them down. The loop rule on the left. The 10 volts over here. So loop on the left. Okay, I didn't mean to write that in blue and red. I'm going to use black. So the loop rule, the loop on the left. We have 10 volts, so 10.0 volts. And that means everything else here, here, here also has to add up to 10 volts respectively. If I go 10 ohms here, then I would have to step down, step down, step down, step down until I come to the other side, 0, and I'm back to 10 when I go through the battery itself. That's just another way of expressing it. Respectively, 10 volts equals 2 plus this plus this. So I'm going to write that down. 10 volts equals 2.0 volts plus the voltage in the resistor in the middle plus the voltage in the resistor on the upper left. Here I can already write a little bit down. I think I'm going to change color. So to abbreviate a little bit, I leave out the 0.0 there. but we keep in mind those are two significant figures because of the 2.0 here and the 5.0 there. Plus, and now what I'm going to do is for the voltage in the middle, I'm going to say I got the current for the resistor in the middle times its resistance, which is 10 ohms, plus the current for the resistor on the upper left times its resistance, which is 5 ohms. And at that point, I may want to define of what I'm saying here is that saying that the 10 volts is applied here and the current would flow this way. Not the electrons, but the electric current. The electrons, of course, flow in the other direction. So I have a plus minus here, and then it splits up into this part. So again, I have plus minus here. Whoops, plus minus. And then I have to see, well, I have to make a judgment. Oh, it looks like 15 is pretty strong here, so probably the current is going to flow through here. And I have plus here and minus, oops, minus there. And then, as I said here on the loop on the left, this one is 10 ohms minus this one, minus this one, minus this one equals 0 coming back here. And of course, when I have minus, minus, minus right here, I put it to the other side, and of course I come up with positive numbers. So all of these three here add up to be the 10 volts. Okay, that's the loop on the left. The loop on the right would be similarly 15 volts here, minus this, minus that, equals 0 all the way back. Respectively, if I get that minus, minus, minus to the other side, I'm going to have 15 volts equals 2 plus this one plus this one. So I'm going to have 15.0 volts equals, let's see what this one is. Oh yeah, there's the 2.0 volts plus the voltage in the middle plus trying to make myself a plus here. There we go. The voltage in the upper right. And again, color change. So I have 15 volts equals 2 volts plus IM times 10 ohms plus I upper left times 10.0 ohms or 10 ohms. There you go. Okay, I explained that if we put these two equations here together, we'll actually come up with the entire loop, and we could write that entire loop down, but you will see that it's redundant, that putting these two equations together yields actually the third loop, the entire loop, and we wouldn't have gained anything. So we have to use one of the junctions, and again, the upper junction makes a lot more sense. Upper or top junction. So the current flows in here and it flows in here, and then it gets together and flows through here. Let's see. By the way, one thing I forgot earlier to say is that with putting these potentials here, plus, minus, plus, minus, minus, plus, I did that arbitrarily because at this point I was just guessing there's probably going to be plus, minus, and then here minus, plus because of the small battery here. But I didn't know that for sure. Actually, I could have looked at my animation earlier and cheated and have that found out that way, but I don't know it. So what would happen if this is actually incorrect here? Well, what would happen is that one of our, let's say this one here would be incorrect, that this one is actually plus and minus. What would happen then is that the current that we come up with would have a negative attached to it, and that would tell me I have to turn it around and come up with the right one. If, in this case, all our currents come out to positive numbers, then I actually have chosen all of three of them correctly. But we can see that later. Okay, anyway, on the upper junction, this one plus this one equals that one. So I upper left plus I upper right equals I middle, is what I called it. Respectively, I'm going to put that all on one side and explain in a little while why. So I put it all on one side. That means that I have 0 equals IM minus I upper left minus I upper right. I know my R looks like a V, but my tablet here is not totally adjusted to give me a nice handwriting. Okay, now I actually need more space. So I'm going to scroll down here a little bit, extend my page, and now I'm going to grab the equations that I have here. Put them all there. 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 I bet that I need even more space, so there we go. Alright. Okay, and now I'm actually gonna get rid of some stuff that I don't need if I just want to look at the equations. So I'm just gonna get rid of the units here, the volts, as well as the ohms. There. But I leave my variables there. And maybe I can make my 10 look a little bit nicer again. Okay, and notice what we have now. We have a system of equations. System of equations with 3 variables or a matrix. In fact, I will write it as a matrix here. I'm going to use yet another color. And still some more space. I'm going to start with the last one first because it looks a little bit nicer to me. Here I'm going to write down, let's see, my matrix. I am on this is going to be the first entry. So it's going to be a 1, I upper L, -1, I upper R, -1. So what I have here is, here's my variable IM, here's my variable IUL, and here's my variable IUR. So 1, -1, -1, as we can see here, 1, -1, -1, and that equals 0. My second equation, well, there's my IM, and there's a 10. There it is. There's my IUL, and there's a 10. There it is. There's no IUR, which means it has to have a 0. And on the other side, we'll subtract the 2 from the 15, which I believe is slightly out of the screen. So subtract the 2 from the 15, I come out with 13. For the first one, IM carries a 10. IUL carries a 5. And I just noticed I must have made a mistake. I'll fix that in a moment. IUR, there is no IUR, therefore it's 0. And then I have 10 minus 2 is 8. Okay, I need to fix my mistake because my middle loop here has to involve IUR, so let me check that. I think that was just a typo. You might have caught that earlier. Yeah, right there. There it is. VUR, and then inexplicitly I wrote IUL. I don't want to record the whole thing over again. If I was in the classroom, I would ask people, as soon as you see me make a mistake, mention it. of course, there was nobody here who could have noticed that. You may have noticed it on your own earlier, but you weren't able to tell me, of course. And as you may recall from algebra, that's actually what happens occasionally with those systems of equations and matrices, that there's so much stuff involved, so many numbers, so many equations, that it's easy to make a simple typo mistake. And yeah, it's kind of, in this case, it's really convenient to just go back and fix it, because all I need to do is take the IUL off here and write IUR. There it is. In fact, I think I'll write it in green so it kind of stands out that I had fixed it. And that also means that this one here is an IUR. There it is. And that means that down here, these two entries have to be swapped. So there's a 0 and there's a 10. And there's a matrix. Whoops. My line came out really strange. So here's my matrix, which I try to solve on the graphing calculator in a moment, which then the way I'm going to solve it is that I get entries here of 1, 1, 1, which are the three variables, and then I'm going to get some entries over here, which of course is going to tell me what those numbers are, each one of them in amps. I actually just noticed that I was supposed to get voltages, but that's alright. I'll just fix that later. And actually it's going to be way more convenient to just determine the electric current and multiply then when I have it here later on with the 5 ohms. But let me grab the graphing calculator. Okay. Let's see, don't need this. Alright. Here we go. Matrix. Edit. Guess doesn't matter which one I use. Okay, it's going to be a, let's see, 3 by 4. Yeah, 3 by 4. And here are my entries. 10, 5. I said earlier I do systems of equations, but then I noticed I actually have 3 equations in 3 variables, and the matrix is going to be easier. There we go. And what was it again? There's 1, negative 1, negative 1, and 0. Okay, done. I get out of this. I look at that matrix on the home screen, and 10, 5, 0, 8, 10, 0, 0, 10, 0, 10, 13, 1, negative, and then negative 1, 0. Okay, then I'm going to go to the matrix, math, and here is what solves the matrix right away, the double REF. And I tell it matrix A. And I'm going to hit the enter button, and I really cross my fingers that I come up with the right result, because if I don't, I must have made a mistake somewhere, and because it's matrix, it's systems of equations, it's going to be tough to find that mistake. So I cross my fingers that I did everything correctly. Here we go. And I'm supposed to, oh no, these are the currents. These are currents. So in the middle current here it says 0.725 amps. The upper left it says 0.15 amps. In fact, I can already see that because I know it has a 5 ohm resistor that I multiply the two, I come up with 0.75 volts. And here it's 0.75 times, yeah, 575 amps. Okay, so that's what I'm going to write down. Those are the amps, the currents. So let's see, 0.725 5 amps. That's the upper middle one. And then, no, not upper, just middle one. It's a long problem. You know, you can say something that's just slightly off, and it does matter. So 0.15 amp, that's the upper middle, the upper left. My goodness. And then this one here is the 0.7. Boy, oh boy. 0.575. I did it correctly, and I want to write it down correctly. So that one is the current on the upper right. And the one that we really need is this one here, which of course is this one here. And what we have to do for that, I think I'm running out of colors, so I go back to black, is that the voltage in the upper left equals the current that I just calculated, I on the upper left, times the 5.0 ohms that was given in the problem, and that equals, well, 0.75 volts, just like we saw earlier in the circuit simulator. So this is the problem on the Wheatstone Bridge, and when we look at it, it kind of looks like these two here are in parallel with each other, and these two are in parallel, and of course this one comes after that, but there's a junction in between. And this one here, if you really think about it, is neither in parallel nor in series with any of the other resistors, and that also means that these here, I said, they look like they're kind of in parallel to each other, but because of this one here, it's really hard to tell. For example, you could say that the current flows through here and through here, so despite the junction here, this could be here kind of in series and parallel with this one. But then again, the current could flow through here and there, and it kind of looks like these two are in series and parallel with that one. So you cannot make a decision on it, and therefore the typical series parallel combination circuit analysis is not going to work on this one here, and it has to be Kirchhoff's rules. I get to Kirchhoff's rules here in a moment, but first I want to put that on the circuit construction kit. Actually, even before I do that, I should actually read what the problem says, and that is, the circuit in the drawing is known as a Wheatstone Bridge circuit. Find the voltage between points B and D and state which point is at a higher potential. Find voltage. Okay, so looking at this one here is actually, this is where we have to find the voltage and where we have to determine which is at the higher potential. Okay, so I'm going to click on the construction kit, and that'll take a moment to open. So this is of course from PhET, Physics Educational Technology, from University of Colorado in Boulder. Alright, grab a wire. Actually I'll grab a number of resistors, and it doesn't really matter if I do it like this or if I do it like it does in there. Actually, come on. It might just make it look look nicer if I do it somewhat like they do in the problem. And once they're clicked together, they're really hard to move. All right. Yep. They just really want to attach here. All right. Okay, now here come the wires. Yep. So there's one. There's one. Actually, didn't have to do it as complicated as I did. This looks actually almost worse than what I tried to do. As far as the aesthetics of it goes. There we go. Okay, I think we can see that this is the way it looks like. Alright, and here's the battery, and I have to check, is the battery to the left or the right? The positive is to the left, so I got it. And then, yeah, that'll be okay. All right. Oh, yeah, and then I have to change all these resistors. 40, 20, 60, 70, 50. So 40, 20, 60, 70, and 50. There we go. Okay, and then I take a voltmeter and I actually put it on here. So there and there, and actually we already got our answer as 0.42 volts with the higher potential here. We can see how the electrons are flowing. There isn't much going through here. Apparently it's, oh, I forgot one thing. Oops, that's 20 volts, not 9. There we go. All right, so actually it's 0.94 volts. Actually, it doesn't matter if I put it here or there. It's 0.94 volts either way. So that's the answer with the positive one here and a negative one here. That, of course, is with the construction kit, but I need to show it the proper way, which is using Kirchhoff's rules. All right, of course, as far as those are concerned, we have a number of loops and we have a number of junctions. And we also have a number of variables. Those variables that we would have would be the currents that flow through each one of these resistors. So we have 5 unknowns, respectively, of course, for each current. Once we multiply it with the resistance, we get the voltage. So if we call these that we have 5 unknown currents or 5 unknown voltages, either way, it's not that we have 10 unknowns, we have 5. There's also a 6th one here, which is the current that flows through here, but I don't want to introduce that 6th unknown, because once I have these 5, I could figure out what the 6th one is. So we'll just leave it out. We have 5 unknowns, the currents that go through here. For these 5 unknowns, for which we technically only have to determine this one, but there's no way around it, we have to find equations that simultaneously compute all 5 of them, and then we single this one out later on. We need 5 simultaneous equations. Well, let's see what we got. We got a junction here, we got a junction here, and we got a junction here, and we got a junction here. That was easy. We have 4 junctions. How many loops do we have? Well, let's look at the triangle here on the left and a triangle on the right, and then we have this diamond here. So those are 3 loops. And then we have a number of loops that actually go through the battery. The top one, so that would be the 4th. The bottom one, that would be the 5th. Then we go through here, watch this, kind of a squiggly one going up. That would be, I believe, the 6th loop now. And then we have the squiggly one going down, and that would be the 7th. So we have 7 loops altogether, and 4 junctions would make for 11 equations. We could use them all, but to figure out 5 unknowns, that would be an overkill, so we would have to focus on just some of them. First of all, what I'm going to do is I label these here. It pretty much according to what we see here with the plus being over here and the minus over here, it would make sense to label these here as plus, minus, plus, minus, plus, minus, plus, minus. Only the one in the middle I would know. I would have to choose plus, minus, or the other way around, plus, minus, because I don't know it to begin with. That's really not known at this point. The other ones are probably the correct guesses. So this one here I have to make a choice. I'm going to choose it like this one here, plus, minus, even though in effect we just saw a moment ago that the positive is at the other end, so it should be actually switched. But what I want to show is when I'm done with the calculation, we will see that the result that we get comes out as a negative, and that negative will then mean switch those two. Okay, so as we go through here, I'm gonna put the arrows on. Let's see, I want to choose maybe a green arrow for the current. So according to what I just chose, the currents are going to go through like this. So lots of drawing, and on second thought I should have actually made this a little bigger, right? Oh well. Okay. Now here are two junctions. Let's separate this here. Two junctions that I'm going to look at, which are junctions B and D. The reason I'm not going to look at A and C is because if I have a current flowing into A and then coming out here, that would mean I have to introduce the total current, which would introduce a sixth unknown, and I want to leave that out, so I'm just going to use B and D. Okay, here's what I'm going to write. Through the junction B, I have a current of I-40 going in, and I have a current of I-60 going out and I-70 going out, and I labeled them here with these here, so I don't have to call them I1, 2, 3, but I call them I-40, I-60, I-70, just referring to the resistance. This number here at this point does not figure in. This is just a current of some value that I don't know yet. So I-40 equals, let's see, I'll write this here. Oh, that'll work. Equals I-60 plus I-70. Okay. Respectively, if I subtract both I-60 and I-70, then I have to subtract them on the left-hand side, and that's what I'm going to do. I'll tell in just a moment why I do that. So I subtract them both on the left-hand side from the I-40. Actually, hold on one moment. Let's start that over again. I put a negative right here, so there's a minus. And yeah, I'll show you in just a moment why I did that. And then, of course, equals 0. The reason why I do that is, having it in this format here, is that I already get kind of my matrix out of this one. You know, the I-20, there was no I-20 and there's no I-50 going into junction B, but I leave a space here so I can come up with a matrix more easily later on. Junction D, there is a current I-20 flowing in. There is a current I-60 flowing in according to my definition. And there's a current I-50 flowing out of it, so actually this would have to read equals I-50, but I subtracted. When I subtracted, I might as well put it right here. Okay, and then that of course equals 0. So again, the reason why I do it the way I do it is that it's convenient, and I will have a matrix here pretty soon. I can readily type it into my calculator and solve it without having further steps that possibly I could make a mistake on. I'm pretty sure that I got it correct right now. Alright, now I need the junctions, and I just had the junctions. I need 3 loops, and among the 7 loops I described earlier, I have to make a decision which ones I want to use. So for the voltages, I'm going to use this triangle here on the left. I'm going to use the triangle on the right. So right triangle, or triangle on the right, and the triangle on the left. Okay. Notice that I will not use the diamond, because if I put the triangle on the right together with the triangle on the left, well, I get the diamond. So that one would be redundant. It wouldn't give me any more information. Then after that, I'm going to use the bottom one through the battery. And notice that if I use the top one through the battery, on top of that, well, then I can just use my triangles together with the bottom one and get the top one. So again, that would be become redundant, and then with the remaining loops, they would be also be redundant if I put the other loops together. So as I said, I'm going to use the right loop, the left loop, and then what I perhaps could call the bottom loop, respectively. I could actually label them. I should label them. Actually, instead of calling them right and left triangle, I should label them as BCD. BCD, that's the one on the right, and ABD, that's the one on the left. And the bottom one is ADC together with the battery. So battery, and what did I just say? ADC. Okay. So BCD, okay, that would mean across the 70 ohm resistor I would have a drop in potential. So I'm going to have negative the voltage at the 70 ohm resistor, which is negative 70 I70. Then I go, so I went here, now I'm going to go this one here, and I have a potential increase. So I have a positive 50 times I50, so 50 I50. And then as I go back to B here, I also have a potential increase, so I have 60 times I60. Also a positive number. And when I'm once around with my loop rule, I come to the same potential, and so therefore going once around, the potential difference is 0, and of course I come up with 0. ABD, potential goes down, so I have a negative 40 times I40. By the way, on any of these where it didn't write a negative in front, that should be a positive. So here it's a plus, there's a plus, here's a plus actually as an equation. Actually here it's kind of better if I do write it, because I still have equations there. Okay, so negative 40 times I40, then this one here goes down, so it's negative 60 I60. Whenever I attempt to write something here, it's just too tiny. It gives me that some kind of circle here on the tablet. Makes it kind of strange. And then I go up here, going back to point A, going up here to through the 20, so I'm going to have positive 20 I20. Okay, and again, once around the loop would come out to 0. All right, now I'm going to go through here, and I have a potential drop, and then I'm going to have going up here 20 volts. Okay, so let's do that. I'm going to have negative 20 I20 and then I go down here, potential drop, negative 50 I50 and then I have 20 going up. Whoops, it wasn't supposed to be a point, but I have plus 20 volts, and that equals, again, I went all the way around 0. Of course, there's no space for the 20 volts here. Notice that everything on the left-hand side is in currents, so I'm going to take the voltage to the other side, and I'm going to write there negative 20 as I do so. Negative 20 volts. Okay. Here are my 5 equations in the system of equations that I have in 5 unknowns, so I should be able to solve them, and it's going to be a whole lot quicker if I do the matrix on the graphing calculator. I'll do that in a moment. Just a word here, if I had used other loops, if I would have written my junctions differently or the loops differently, as long as I do it correctly, I would come up with the same result. So this particular system of equations is not unique. I could write it differently depending on if I had taken my loops in a different way, but the result at the end will be the same. So if you do it slightly different on a different problem, don't worry which loops you're going to take, which junctions you're going to take, because you will come up with the right result as long as you do the algebra and the math right. Of course, again, here I didn't choose this particular junction here because it would have introduced a 6th unknown. Alright, so let me extend the page, and I can readily write this as a matrix. And let's see, I need enough space here. Will some of this be a little bit? Well, might be just a little bit out of the picture. Alright, so here I have a 0 and a 1, a 0, negative 1, negative 1. I'm looking to the very top there, 0. This is kind of where I'm running out of space. And then I have a 1, 0, negative 1, 1, 0, 0. And then for the loops, 0, 0, 50, 60, negative 70, 0, 20, negative 40, 0, negative 60, 0, 0, and I scroll this a little up, negative 20, 0, negative 50, 0, 0, negative 20. Of course, somebody could say on the last one I might as well get rid of the 0 negative on each one of these, but oh well. Let me just double check that. So I have, here's negative 20 down, negative 50 down, and then here's the, yeah, that's actually 20 up, but it would be on the left hand side. When I get to the right hand side, it would be negative. Then this one here was the loop on the left hand side, so that was because I went this way here counterclockwise, it's 20 up and it's 60 down and it's 40 down, slightly out of the picture. And then on the right hand side, that was I went counterclockwise, so that would be 50 up and 60 up and 70 down. And then the junctions would be the junction D, the 20 is going in and the 60 is going in and the 50 is going out, so that's why this one here, and then that would be on the other side, so I have to subtract it, becomes negative. And a junction B, this one is going in, so that's positive. These two are going out, they would be on the other side, but I have to subtract them, and that's where negative 1s are. Alright, graphing calculator. If you don't have a graphing calculator, you may have to go the hard way of doing these here as simultaneous equations or on paper. I have the luxury, and many of us do have a graphing calculator for this class because in algebra it was already required, and a trick you might have used them also if you have already taken trick. Alright, let's do this one here. Actually edit, go one down. I think this is a 5 by 6, and now I have to see 0. Plug in all the entries. Okay, so I just put in 30 entries, and I cross my fingers that I put them in all correctly. Let me see. Yeah, the first column looks correct. The second column looks correct. The third one looks correct, as long as I didn't make a mistake on paper. The next one looks correct. So on 30 entries, you know, what's the probability on doing something incorrectly? Probability is higher than if I only had them plugged 2 or 3 numbers, but I had to plug in 30. Okay, let me give it a try. What do I want to do? Oh. Okay, I calculate, and that's a double REF. There we go. And there we go. And I go over here, and the one that I was supposed to compute is the one in the fourth one. So the 60 for the 60 ohm here, and this one here is negative 0.015625. That's the electric current that goes through it. Multiply that by 60. So I'm going to do negative 0.015625. Again, I was supposed to look at the I-60 here, the one for the middle one, and that of course shows up here right there. There's that variable and comes out right here, and that's the current in amps, and I have to multiply that with 60 ohms to get the voltage, and just like I showed on FET earlier, that's negative 0.94 volts. So here I'm going to write, let's see what color. This one here is going to give me I equals so many amps, and from that I'm going to get that volts equals, actually I should say 60, there we go, voltage equals I60 times 60 ohms, and that equals, well, the negative 0.94 volts, and that negative then tells me that this one here actually needs to be turned around. So actually this one here is a positive, and this one is a negative, and then this one here, the current actually flows in that direction. That's what that negative told me. Long problem because the Wheatstone Bridge is not easy. It takes quite some effort and time and algebra skills. And I'm glad I'm able to do this in a matrix, because you could imagine if I tried equations, elimination, and substitution, this would have taken way longer than the 28 minutes that I have on the clock here.